Welcome to our today's webinar. Today's topic would be the dilatometry, an overview about our dilatometry instruments, and some measurement examples. The complete webinar will be recorded, so afterwards you can request the video of the webinar, including questions and answers. So in case you miss something or you have sound or video issues, don't worry, there will be a recording and you can have the recording. We will have a short discussion after the presentation. So if you have questions or if you want to say something or want to know something, please type your questions into the chat. So there's a chat function and there's also a question function that you can use. We will answer and discuss this after this presentation. So if you want to discuss and have questions, please stay after the presentation. I'm just waiting for 1 more minute to let some people join, and then I will start the presentation. As said, you will all be muted, so you will not be able to talk. You just can type questions and answers into the chat. There are still some people pending. I hope they can join. Yeah, looks good so far. Okay, I think we are more or less complete for the moment. So again, welcome and thank you for joining this webinar series. As I already said, the webinar will be recorded for all the participants who are interested. There will be a recording and video available afterwards. In case you have sound or video issues during the talk, don't worry, you can have the recording. If you want to discuss or if you have questions, please use the chat function, type your questions into the chat. We will discuss that after the presentation. Meanwhile, we are quite a few people, so I think I can start. As said, today's topic is dilatometry, an overview about our instruments and techniques. First of all, I like to introduce myself. My name is Sebastian Seibt. I'm the head of laboratory in our application lab at Linseis headquarters in Germany. I'm a chemist, studying chemistry until 2013. Then I joined Linseis, and since then I'm working in the lab. Meanwhile, I'm the responsible person for our testing, service testing, and application laboratories. I can speak the languages German and English. So if you have questions or if you need some measurements or if you have questions regarding configuration about instruments, you're always invited to get in touch with me directly. You can reach me using this email address here, or you can just ask for me if you contact us directly via webpage or social media. So that's me. For those who do not know the company yet, some short sentences about the company. Linseis was founded in the 1950s by Dr. Maximilian Linseis in Seibt, where our headquarters still is located. We manufacture in Germany mainly, and we distribute our instruments all over the world. At the moment, we have facilities in the US, we have facilities in China and India, where we have our own sales and service offices. We can do maintenance there, we can do installations from there, and we also have labs meanwhile spread around the world, because sample shipping around the world takes too long. So therefore we can test samples in US, in China, in India, and of course here in the lab where I am placed or located here in Germany. In the meantime, we are in the 3rd generation. So the son of Dr. Maximilian Linseis, Mr. Klaus Linseis, is the owner of our company, and his 2 sons are in charge of the daily business. So Florian Linseis and Dr. Vincent Linseis are the 2 guys who are running the company. They are spreading this a little bit, like Florian is doing the sales and marketing and Vincent is doing the development in our company. And yeah, that's where we are at the moment. We have around 150 employees all around the world, and our main business areas are the manufacturing of thermal analysis instruments and of course service measurements in our service labs all over the globe. On the pictures at the lower right side, you can see one of the data loggers, one of the products Linseis started its business with in the 1950s. And on the right side, you see the actual dilatometer lab here in Germany. So that's a little bit about the company for those who are not aware. Regarding the product range, as I just mentioned, we are manufacturing any kind of thermal analysis equipment. That means we cover the full range, beginning with classical thermal analysis. So we have multiple calorimeters, mainly differential scanning calorimeters, so-called DSCs. in different shapes for a complete range from liquid nitrogen temperature up to 2400 centigrades. They can also be combined with thermobalances, the next product in line. So thermobalances is also a typical classical instrument where you can measure the weight change of a sample during heating, during cooling. And the combination of DSC and thermogravimetry would be a so-called simultaneous thermal analysis. Besides that, our today's topic where we will focus on is the dilatometry. We have multiple dilatometers, as you will see in the next slides. Also covering a complete temperature range from liquid nitrogen, liquid helium even, up to ultra high temperatures in graphite environment. And yeah, that's what we will discuss in the next slides. Besides that, we have thermomechanical analyzers for determining Young's modulus and stuff like that. We have fields like thermal conductivity, thermal diffusivity, where we have multiple instruments that will be presented in one of the other webinars soon. We have instruments for thermoelectrics, and in the more recent past, we are focusing a little bit on thermoelectrics and thin films, so analysis of coatings, thin layers, paints, microchips, computer chips, stuff like that. We analyze Hall effect, and we also do a lot of optimizations, high pressure instruments like coupling with different gas analyzers, doing customer requests and customer optimizations. So that's what we are mainly doing here. Coming back to the topic, the dilatometry is what we are talking about mainly today. So the dilatometer is one of the oldest thermal analysis instruments. It all started with a push-rod dilatometer, which is a system like this. The picture down here shows the schematics of a typical push-rod dilatometer, which consists of a measurement head on the left side and a furnace on the right side. Within the furnace, there is a heater, of course, and there's an inner tube. And within the inner tube, you see this red sample piece. Usually, this red sample piece is placed on a sample holder, which is this transparent rod you can see here. And within the sample holder, there is a movable push rod, this yellow part here. This push rod goes from the hot furnace zone through a flange into the measurement chamber. The measurement chamber is usually thermostated and kept isothermal at low temperatures, so around 30-40 degrees. So the conditions here should be stable. So somehow you get rid of the heat of the furnace in this middle part. And the measurement system more or less records the movement of the sample when the sample sees some heat or some cooling or any kind of temperature change. And this is what you do. You basically record the expansion or the shrinkage of your sample. So this is just the basic principle of a dilatometer. Of course, there are multiple different ways to build it, set it up. The drawing you just saw fits to the standard horizontal dilatometer you see up here. It's called DIL 7576, which is our basic series. This series can be used horizontal, like you see on this first picture. It can also be used vertical. I will explain the difference and the advantage and disadvantage on the next slide. Just keep in mind that the standard configuration is available as a horizontal or vertical setup. These are our standard push-rod dilatometers, and besides that, we have different special versions. We have so-called optical dilatometers, where you have a furnace without push-rod. It's a furnace where you just place your sample on a little platform, and you close the furnace, and then you detect the expansion and shrinkage no longer by touching it with a mechanical push-rod, but you measure the expansion with a camera setup. So you have a high-resolution camera detecting the edge and the shape of the sample and measure it contact-free. The setup was optimized for sintering studies where a force or physical touch could be a disadvantage. Therefore, you can measure it completely contact-free and then can have a sinter study or melting study or stuff like that. For quality control issues and for high throughput, we have quattro, so-called quattro dilatometers, which is a system that can measure up to 4 samples simultaneously. So you have one furnace, and in the furnace you have 4 sample positions and 4 push rods. This was designed for high throughput quality control, and you can measure 4 samples at the same time using different furnaces, even so you can have a high or fast throughput. And then we have dilatometers for special applications, like the quenching and deformation series. We call it RITA for rapid inductive thermal analysis. It's an inductive dilatometer for the steel industries. It can heat up metal, or especially steel samples, very quickly and simulate a forging process or simulate a firing process. You can reach 1,000 or 2,000 centigrades within seconds here, and you can also cool it quite fast within seconds using helium, expanding helium gas. And therefore you can create phase diagrams and 3D phase diagrams of steel phases and of different metal phases. So it's something, very special, but quite useful. Then on the next picture, we have a pressure dilatometer. It's also a very special customized system where we have dilatometers that can operate under pressurized atmosphere. It was for sorption studies where the expansion and shrinkage of an adsorber should be detected. And therefore we have now these pressure dilatometers in the catalog, which is something very unique and very rare. And besides that, we have some other special versions that are usually sold not that often, but we have them, which is the laser dilatometers for ultra high precision. It's a push rod with a laser within the push rod that measures the exact distance between measurement system and sample using interferometers, obtaining the highest possible resolution. We have cryodilatometers or cryodilatometer series where we use liquid helium. I will show you also. So using the liquid helium, reach temperatures up to 10 Kelvin. We have macrodilatometers for very big samples, and we have a special configuration for nuclear samples where you separate the electronics from the furnace more or less to be able to run under very corrosive, very toxic, and irradiating atmospheres. So that's the complete range that we offer. As I promised, I will just go into detail and explain a little bit the differences and advantages and disadvantages between the different versions. Starting with our standard configuration, horizontal and vertical setup. So the L75 and 76 series, our push rod dilatometers can be horizontal or vertical setup. The horizontal setup can measure 1 or 2 samples simultaneously, automatically adjust the pressure between push rod and force, between push rod and sample, I'm sorry, and you can set the force up to 1 Newton. The same in the vertical setup, you can measure 1, 2, or 4 samples, and you can also automatically adjust the force between sample and push rod. The advantage, or the clear advantage of the horizontal setup, it's quite easy to handle. You just put your sample with the tweezer from the top into this sample holder you see on the top left, on the down left picture. It's quite easy to handle. It's user friendly. It's really simple. It's the perfect choice for mid-temperature ranges, I would say up to roughly 1000 centigrades. It's, as I said, easy to handle, and it can be customized for bigger samples, customized for special samples, sample geometries or diameters. On the vertical setup, it's a little bit more complex, or a little bit more difficult to insert the sample properly. Usually you place them on the push rod, so the sample is standing on the push rod, and then it's clamped between the push rod and the end plate over here. In the vertical setup, we have up to, as I mentioned, up to 4 rods at the same time. Usually it's 1 or 2, but we also have the quadro with 4 rods. So the handling is a little bit more complex. However, you gain some advantages. First of all, in vertical setup, you have no friction. So the sample is standing between push rod and end plate. It's not touching the sample holder. It's completely freestanding. So you have lesser friction. Just in case you have a sample that's reactive or has a reactive surface, it will not bake on the sample holder. It will not be in touch with the sample holder. You get a more clean signal. You can have multiple furnace arrangement, but that you can have in both setups. In the vertical, it's up to 3 furnaces, and the horizontal is up to 2 furnaces that you can turn around and switch. So you gain 1 more furnace position in the vertical setup. And if it comes to very low or very high temperature measurements, just in case you have 2000 centigrades or even higher furnaces, or you want to measure lowest liquid helium or liquid nitrogen temperatures, the vertical setup is the perfect setup because you get rid of all the convection, because hot gases always tend to go up, and therefore a furnace for ultra high temperatures should be on top in the vertical setup, and a furnace for ultra low temperatures usually is on the bottom side. So it's flipped around. If you go to low temperatures, usually the furnace is on bottom side and the sample detection system is on top. So with the vertical setup, you you have a little bit better temperature spread, you have more homogeneous temperatures around the sample, and the measurement is a little bit easier if it comes to very high and very low temperatures. So that's the main or the key difference between these two basic setups of our basic two instruments. Regarding the detectors, speaking about basic instruments, regarding the detectors of all our dilatometers, we have two different ways or two different approaches to get a sample reading. First of all, most of our instruments work with a classical so-called LVDT, so a linear differential transformer, or basically an electric magnet. On the right side, you see a picture. On the left side, you see a schematic drawing. How it works, it's quite simple. You have a core that's connected somehow to a pushrod. So if the pushrod moves, this black core will be moving in the one or the other direction. And then you have a primary and two secondary magnetic coils. And these coils will create voltage if the core moves. So out of this voltage shift, you can directly monitor the movement of the core as an electrical signal. It's an easy way to transform movement into electrical signals. And out of the signal, you can calibrate it. You can get a reading in nanometer range, how your sample behaves and how your system behaves. That's how it's usually working. It's as easy as it looks like. And this technique is known since like 50, 60 years now. Besides that, we also offer optical encoders. As an alternative to the LVDT system, there are optical encoders. In that case, you have this actuator plate, this black plate. It's also in touch or somehow in touch with the pushrod. If the pushrod moves, this black plate, this face plate here, where the light comes in, sees a movement of this black actuator plate, and this phased light that comes from this light source here will create a different hitting on the detector, a different signal on the detector. So these little light beams here are phase shifted, and the detector sees a phase shift due to the movement of this actuator that's semi-transparent. And out of this, the detector gets a reading in what direction it moves and how much it moves. The resolution is more or less the same. It's also nanometer range. And there are just a few slight differences between these two. So the main difference is the LVDT, of course, is limited by the length of the magnetic coils. If the core moves out of the magnet, that's the limit of your measurement range. In our dilatometers, our magnets are usually operating in a range of plus minus 5 millimeters. So that's not that much, but as the expansion comes in micrometer, nanometer range, plus minus 5 millimeters is fine. It's fair enough. So that's the limitation of the magnet. In case of the optical encoder, this actuator plate can be infinite long. In theory, you can use a centimeter long actuator plate, so the range can be bigger. During the measurement, that doesn't matter because usually the measurement just measures a few microns, so you do not need that long range. However, if you want to determine the L0 of your sample automatically, the LVDT will not be able to measure the exact absolute length of a sample. However, with an optical encoder, you can do that. For that reason, meanwhile, we equip our LVDT systems with an additional encoder system to measure the absolute length of the sample initially, but then monitor the movement during the measurement using an LVDT. Why we do this is because we noticed that a LVDT is robust. The magnet is not affected by dust, by gases, by anything, so it measures always properly and it works. If you measure samples that show some outgassings, if you measure samples that create dust, we just don't care. The LVDT works. Using the optical encoder, it's a little bit a disadvantage that this encoder plates are very dust sensitive, are very sensitive to pollutions. So if there's some dust, if there's some particles, if there's something hitting this actuator plate, you will not be able to read out the expansion signal anymore properly. And then you have to clean the system. Therefore, you need special tools. You need to send it to the manufacturer. You need to clean it in a clean room, maybe. So that's cost intensive, and that's not good, not user friendly. That's why we usually focus on using LVDTs. However, if somebody wants an optical encoder system as a standalone detection system, they are available on the market, so you can just buy one, purchase one. So we can offer a system using an optical encoder as well. However, just keep in mind that maintenance may be an issue here. That's what you need to know. So far about the detection systems. And then we have measuring systems that are very flexible. So the sample holders and the push rods can be made of different materials. That means our sample holders usually are made of quartz. For higher and lower temperatures, we have different systems. For high temperatures, we have aluminum oxide or alumina systems, where the push rod and the sample holder are made out of alumina. We also have systems out of tungsten and of quartz. If a customer needs a special setup and a special material, we can also design these sample holders and rods out of special materials that customers are requesting. You need to know that quartz and glass systems are very user-friendly again, because they do not show very much own expansion, so you can use them as they are. For all other systems, you need proper correction curves. You need to run curves with the system without sample to get an idea how much the system itself will expand and behave under the corresponding temperature profile. Otherwise, you will have a measurement error. With quartz and glass systems, you do not need to do that, because the expansion of the glass is so small that you more or less can ignore it. For all these setups, there are different inlets and inlays. So we can have adapters for powders, paste. We also have a liquid adapter on demand that can be inserted between push rod and sample holder. And then you can also measure powders, liquids, pastes, gels, whatever you have. So that's where we are quite flexible. And also these adapters can be made of different materials, but that depends on the application and the sample type of the customer. And again, as you see, we try to keep it quite modular. We are also quite flexible regarding the furnace. We have a quite broad range of furnaces that are on stock or more or less available, starting with liquid nitrogen metal furnaces, going from liquid nitrogen up to 1000. Then we have furnaces that work from room temperature up to 2800 if it's a graphite. We also have tungsten furnace on demand. We have platinum furnace on demand, and we also have cryostats, but that's not a furnace, that's a cryo system for liquid helium temperatures. We can offer all these furnaces to almost all our dilatometers. They differ a little bit in the heaters they use. They differ a little bit in the atmospheres they can withstand. So up to 1600 or 1700 centigrade, we can use almost any atmosphere, no matter if it's vacuum, reducing, oxidizing, inert. Also reactive atmospheres are possible. If the customer tells us upfront what kind of setup he needs, we have the proper setup. The atmosphere you're using defines a little bit what kind of temperature sensor you can use, because usually in a dilatometer you have a temperature sensor directly in touch or close to the sample, and this temperature sensor usually is a thermocouple. We have different types of thermocouples out of different materials. They cover different temperature ranges and they cover different atmosphere. So usually we have type K or type S. However, if you want to run in hydrogen environment or in carbon monoxide, carbon dioxide, maybe you use type C or type K. It depends a little bit on the combination of temperature range and desired atmosphere. But as said, our furnace and temperature sensor program is quite flexible and quite modular. So one can configure its own dilatometer, depending on his needs. So as said, we try to keep that as modular as possible. Besides that, the modular standard program, I also promised to have a closer look at the special versions. So I will just introduce all the special versions that we have, beginning with the heating microscope and optical dilatometer. We have this contact-free optical system where we have a sample holder that's just a platform where you place your sample on. And then you have a high-resolution camera system that can operate in two ways. On the left side, you see the so-called heating microscope mode. Using that mode, you have no filters, you have just the camera, and the camera has a viewing angle of 2 × 2 centimeters. So you see the complete sample piece, and then you record the sample piece completely, so in 2 dimensions, X and Y axis, during heating, during cooling, whatever you do. Typically, it's melting studies, it's contact angle and surface wetting studies. So you see in that example here, a sample that's melting. First of all, it gets a little bit softer, then it starts to melt, it starts to form a sphere or a half sphere. before it starts to melt really down and wet the surface. The system can detect the angles between your sample and a defined platform. Either you use an alumina plate, which comes with the system, or you can also use any kind of substrate plate if you want to investigate the wetting between a sample and the specific substrate. You can place a substrate plate in there, put the sample on top, and melt it onto your substrate. And so you can measure the wetting angles, contact angles, temperatures when it melts, temperatures at which the sample wets the surface. So this is the typical heating microscope mode. The heating microscope mode has a resolution of several microns, so it's not an expansion measurement anymore, it's more geometry shape detection. On the other hand, the system has a real dilatometer mode. In that case, you just look at the very close upper edge of the sample in a just some millimeter broad image view. So as you see on the right picture, usually you have a sample next to a reference body. The reference body is a reference body that comes with the system, is provided from us to correct the expansion factor because of the atmospheric changes in there. And the system then automatically recognizes the shape or the border between sample and background. Therefore, we have a polarized light source at the backside and some polarization filters in front of the camera. Out of this, you get a pretty good resolution of this edge. And then you monitor the movement of the edge over temperature, providing a resolution of roughly 0.5 up to 1 micron, which is not the range a dilatometer with a pushrod can reach. However, it's very close to the limit of optical wavelength path. So you get a proper reading for most samples. Of course, if you have samples that only show very, very narrow expansion nanometer range, the optical system will not be suited. And that's how it is. The next instrument of our special instrument series would be the quenching dilatometer. As said, it's an inductive system. It is available as heating and cooling only, or with an actor for deformation studies. Here, the setup is a little different. So it's again a pushrod system. You have quartz pushrods that are touching the sample. You can also have ceramic pushrods for higher temperatures. And the sample is clamped between two pieces of rod. And then there is a magnetic coil with a magnetic field generator surrounding the sample. If you apply a magnetic field, modular magnetic field, so it can be adjusted, you can reach very fast heating. So it's induction controlled. So the temperature of the sample is monitored by this thermocouple that's in touch with the sample directly. You measure the heating, and out of the heating of the sample, the system can very fast regulate or control the power of the magnetic field and the power input. Therefore, you can create any kind of temperature profile, and you can heat and cool in very, very short times. The cooling is achieved by pushing expanding cooled helium gas through this coil. So this hollow coil has this little black holes here where the helium gas can be brought to the sample quite quickly. So you can really heat and cool the sample within seconds. In case of the deformation setup, there's an actor, and the actor can actively deform with some kilonewtons. So if you can heat it up fast, you can also apply very high forces to simulate a forging process, simulate a mechanical process quite properly. As said, we reach rates up to 1000 centigrades per second heating and up to 400 centigrades per second cooling, which allows the creation of CCT, CHT, and TTT, so controlled temperature profiles, so 3D phase diagrams. This complies with the ASTM standard A1033, which is very, very special, and it's a steel industries standard. But for all these forging companies, steel manufacturers, this is very crucial information, and we sold quite a lot of instruments out of this series. And by the way, we are one of 2 manufacturers worldwide that offer that kind of system. That's a very special form of our dilatometers. Then we have other special instruments that are very customized. First of all, we have the so-called helium dilatometers, where we have no furnace, but a helium cryostat, where we have a liquid helium cooler, allowing us to reach more or less 5 to 10 Kelvin. We can reach a controlled cooling rate up to 0.5 Kelvin per minute, down to roughly somewhere between 5 and 10 Kelvins. Depends a little bit on the sample. That's why I'm saying roughly 5 to 10. 10 is what we reach for sure, 5 in case the sample is proper. So we can reach that range with 0.5 Kelvin per minute, and we can also heat up with 5 Kelvin per minute, and the system can heat up to 200 centigrades, even if it cools so much down. And that's a very unique system that was ordered by some special customers, like you see here. They are using this in terms of research for satellite techniques, rocket techniques, if you want to simulate the space conditions with close to absolutely zero temperatures. And we have customers from the computing area where they are doing research on quantum computing and stuff like that. So that's where we sell this very special kind of instruments. And the last special configuration I want to introduce to you is what we sold quite frequently in the more recent past. It's instruments for nuclear applications, where we have a separation of control panels and electronics from the measurement setup. So as you see, what remains is just the furnace, the rod, and the little actor that moves the rod. And all the electronics, the computer chips, readouts, and so on is separated completely. That means you can place one part in a hot cell, glove box, or in a hot environment, and you can control and maintenance the system from another room, from a space that's more or less safe. We have variable feed-throughs. That means we can adjust and adapt the system according to your needs. And we sold that for nuclear fuel. That's a typo. So nuclear fuel research and for corrosive and toxic environments. So we have customers working in fluorine gas atmospheres, which is very dangerous, or carbon monoxide atmospheres. And then you can maintenance the system without the need of accessing it. Most of these systems are operated by robots or by glove boxes. So that's also something we can adjust. And it's a quite frequently asked setup indeed in the last years. So that's the last special version that I want to show you. I'm sorry, I forgot one. I was asked to mention also that we meanwhile build macro dilatometers. So the dilatometers you just saw can also adjust it to macro samples meanwhile. That means we have a maximum sample diameter of 50 millimeters meanwhile possible. And that was sold twice now for customers who investigate graphite cathodes and very inhomogeneous materials where you need very, very broad and big samples. So our maximum sample size is meanwhile 50 millimeters diameter, 100 millimeters length. Of course, if you want to investigate such big samples, you must be aware, or you should be aware, that you can only operate with very, very slow heating and cooling rates. Otherwise, the temperature of the sample would be very inhomogeneous. But just to mention that, this is possible for the standard series of dilatometers. Meanwhile, so we have this macro dilatometer, and our standard configuration can be brought into the macro shape as well. Okay, but now that's it for the special configurations. I want to give you a short overview about the typical applications before I close this presentation. So all I showed you now was all dilatometers, and they were all, or most of them were customized and had a special application field. So as a summary, the typical applications for the dilatometers are, of course, detection of the thermal length change, determination of the coefficient of thermal expansion, which is the value that most people want to get or want to obtain if they use a dilatometer. We can measure the expansion by volume. If you have liquids and powders or even solid bodies, we can measure volumetric expansion. We can do sintering studies, which is one of our main fields. And some other applications would be detection of softening, melting points, glass transitions, or phase transitions during or without mechanical force, during forging process, during ceramic manufacturing, and also during additive manufacturing and stuff like that. I have some typical curves that the dilatometers would give you. So first of all, this is what a classical push rod dilatometer measures. The example here is a standard glass sample. What you see is the linear or more or less linear expansion of a glass sample up to the softening point. You can see here, if a glass comes close to the softening, it suddenly changes its expansion coefficient. It suddenly starts to expand very fast and then goes through a little peak before it starts to get soft and melts. And that is a typical look of a glass expansion curve. Just as an example for a typical dilatometer. You also can do calculated DTA, which is something very special or very, very new. If you set a temperature profile and you measure the temperature of your sample, if the sample undergoes a phase transition, you can only see an expansion change. You can also see a change in the actual temperature of the sample. You can sense that. And if you compare the sensed temperature with the actual program temperature, you can calculate that kind of temperature difference out here, which is more or less a calculated differential thermal analysis, like you would use a DSC, where you would use an empty crucible and the sample containing crucible and measure the difference. Here you can measure the difference between program temperature, and out of this you can have an idea of a reaction P. It's not a real DTA and the quality is more poor than a DTA, but if you do not have a DSC or DTA available, you have an indication and a hint how that might look like. Another typical example of our dilatometers would be ceramic sintering. That's something also very frequently measured. So we very frequently get ceramics, bricks, and in that case, it's a brick sample before and after sintering. So in that case, customers are usually not interested that much in the CTE, but in the temperature when the sintering takes place and how fast it takes place. And people want to optimize these sintering behavior. So the sintering speed should be optimized. So usually we have also rate controlled sinter studies, so where the software automatically adjusts the heating speed depending on the needs and the required shrinkage speed of the sample or sinter speed. So in that applications, people try to minimize the holding times, minimize temperatures, but the sinter speed should be within certain limits to make sure that the sample does not get damaged or does not get brittle and so on. So it should sinter properly within time, but people are just focusing on optimizing the sinter temperature and sinter duration. And that's what you can typically do with all of our dilatometers. We also did hydrogen sintering. So the complete sinter study can also be done in hydrogen atmosphere. As I said, most of our instruments can be used in reactive atmospheres. Something very typical would be additive manufacturing. So you get metal powders, compressed metal powders, and then you do the metal sintering in hydrogen or reducing atmosphere. And what you see is more or less the shrinkage, the absolute and percentile shrinkage of a sample during heating. Usually a sinter study has a very defined temperature profile. So you have heating, you have isothermal segments, followed by heating, another isothermal segments. And during this, the sample should undergo its sinter process. That's just an expansion of powder samples. That was the softening of a powder. So when you measure emile powders or when you measure powders, you have to be aware that the density of the powder is an issue. So usually you measure with constant force. Our dilatometers can measure with constant force. And under constant force, a powder has a certain grade of compression. And when it undergoes softening, and the force stays the same, but the expansion suddenly goes down because if the sample gets soft, the same force that was able to keep the sample in place before now compresses the sample at a certain temperature. And that's a kind of powder sample, or just one example for a powder study. Then I have some typical examples for the special configurations. This measurement here is the expansion of a graphite sample with a 2800 centigrades ultra high temperature graphite dilatometer. Let's ask if it comes to cathode research, if it comes to graphite research, and some very special metals require that kind of temperature range. It's just to show you that we can really go up to the 2800 with a graphite furnace. It's nothing special. It's just an example for that kind of measurement. I also have an example measurement for the helium cryodilatometer. This was a copper standard sample. And what you see here is the temperature, and the blue curve is the expansion of a copper sample. So we use that for the cryodilatometer, cool it down up to -250 centigrades, showing linear shrinkage and linear expansion, just as a proof that we really can reach these temperatures. What's interesting is that if it comes very close to the absolute zero, a lot of metals and also this copper sample shows some non-linear shrinkage and non-linear expansion effects that are occurring down at the very low temperature range, and that's the reason why people are investigating that range. This is how a measurement on the quenching dilatometer would look like. So you can measure very fast heating and cooling, and this is a phase transition of a steel sample. So what you see is during fast heating, there is a phase transition, and during cooling, there's the back transformation, and the exact temperature where these transformations happen depends on the heating and cooling speed. If you cool down very slowly, the temperature will be, the transformation will be shifted, and out of the cooling speed, out of the heating speed, you can determine and define what kind of phase you will get at room temperature, and that directly influences the hardness of your steel, the behavior of your steel, if it's soft, if it's brittle, if it's stiff, and that can be determined using heating and cooling diagrams like this. If you do this experiment multiple times at different speeds, you get this kind of 3D diagram giving you zones and phases and defining you how fast you should heat and cool to obtain a certain steel phase. As said, for steel industries, that's very crucial information, and that's a known topic for itself. But somebody out of the steel research industries can explain that a little bit more in detail and a little bit more properly than I can do it. Just for you to know that we can do that, and that's what we can offer. So far about our dilatometers. Thank you for joining this presentation. Thank you for your attention.